A binary search tree is a special type of a binary tree. Specifically, a binary search tree has these three properties. First, it has to be a rooted binary tree. So there has to be a root, and every node can have either 0, 1, or 2 children. Right? So rooted, it has to have a root, and it has to be a binary tree. And then for any given node, every node must be larger than every single node in its left subtree. So given some node, it has to be greater than all the nodes in its left subtree. And similarly, every node is smaller than all nodes in its right subtree. So it should be less than every single node in its right subtree. This is a little abstract, so let's take a look at a specific example. Let's say I have the following tree. I can have maybe a root that is 10. I can have maybe a left child that's 5. Maybe a right child that's 15. Maybe this has a left child that's 2. Maybe this is 7. And let's say this one has just a right child that's 20. And then maybe a left child that's 17. So this is an example of a valid binary search tree. It's rooted, this is my root, and then everything else goes downwards. It's a valid binary tree. Nodes either have 0 children, 1 child, or 2 children. And then for every node, so every node is larger than all nodes in its left subtree. So 2 doesn't have any left children, so that's fine. 5 is larger than 2. 10 is larger than 2, 5, and 7. 15 doesn't have any left subtree, so it's fine. 20 is larger than 17. 17 doesn't have a left subtree, so it's fine. And every node is smaller than all nodes in its right subtree. So 10 is smaller than 15, 20, and 17. 5 is smaller than 7. 2, 7, and 17 are all leaves. They don't have any right subtree, so those are fine. 15 is smaller than 20. And 20 doesn't have a right child, so it's fine. So all three of these properties are maintained. Let's take a look at another tree that's actually not going to be a binary search tree, but it's a little tricky to find out. So let's say I have 10, I have 5, and let's say over here I have 20, and then here I have 9, and maybe 30 here. So one thing that I want to emphasize, which is why I'm drawing this specific example of not a BST, is that a lot of times when people try to see if a given tree is a valid BST, they'll just look locally at any given node and make sure that it's bigger than its left child and smaller than its right child. But it actually has to be bigger than every single node in its entire left subtree and smaller than every single node in its entire right subtree. So in this example, 10 is bigger than both of it, than its left child, and 10 is smaller than its right child. 20 is bigger than its left child. 20 is bigger than is smaller than its right child. And these three don't have children, so they're fine. But this is not a binary search tree because of the relationship between 10 and 9. 10 has 9 in its right subtree, but 9 is smaller than 10. Therefore, it invalidates rule number 2. Rule number 3. 10 is not smaller than every single node in its right subtree. 10 is not smaller than 9. So this is not a BST. So I wanted to show this example just to emphasize when you're checking if a given tree is a valid binary search tree, you have to look at the entire left subtree and the entire right subtree of a given node. It's not sufficient to just look at the left and right child of a given node.